Houston, we have a podcast. Welcome to the official podcast of the NASA Johnson Space Center, episode 17, Orion. I'm Gary Jordan, and I'll be your host today. So this is the podcast where we bring in the experts, NASA scientists, engineers, astronauts, all to let you know all the coolest information about NASA. So today we're talking about the Orion spacecraft with Najud Moranci. She's the mission planning and analysis lead here at the NASA Johnson Space Center in Houston, Texas for the Orion spacecraft. And we had a great discussion about Orion, what it is, how it will work, and where it's in space it will bring humans to explore. So with no further delay, let's go light speed and jump right ahead to our talk with Mrs. Najud Moranci. Enjoy.
Minus 5 seconds and counting. Mark. Launch commit lights are correct. There she goes.
Houston, we have a podcast.
Okay, well, Najud, thanks for taking the time to come on the podcast. Honestly, kind of surprised that we haven't done an Orion episode so far. I mean, we've hinted at it, but we really haven't gotten down and said, what is Orion? So thanks for coming on today.
You're welcome. Glad to be here.
Absolutely. So honestly, that's kind of what I wanted to do today, is just kind of hone in, what is Orion, the general overview. So let's just start with that. If you could describe it in a nice kind of overarching bird's eye view, what is Orion?
Orion is supposed to be America's next crew vehicle for beyond low Earth orbit.
Okay.
So really the point is to return to exploration, which we really haven't done since Apollo days, right?
Mm-hmm.
We had the space shuttle and the space station, and they're doing amazing science and research, but they stayed in low Earth orbit. So
right.
To actually get out of low Earth orbit is a challenge we haven't had in 40 years, and that's where Orion and the Space Launch System rocket comes in.
All right. Okay, so yeah, we could talk a little bit about both, but Orion is the spacecraft. That's the one that's actually going to carry the people.
Orion has the people.
Yes.
And of course I'm Orion, so we're the most important, of course.
All right, so let's just focus on the most important part then, right? Let's focus on Orion. So, I mean, what does it look like? If you had no idea what Orion looked like, how would you kind of describe it?
So Orion's got several pieces, so each one is a little different, right?
Okay.
When you stack it all together, we have a launch abort tower on top, so that's only there for the first part of ascent.
Okay.
But we get rid of that once we're higher enough up in the atmosphere that we don't need it. But when you get down to it, what the pieces that will actually fly in space look like is a capsule shape, very similar to Apollo. We're actually using the same angle on the back shell that Apollo did.
Oh, wow.
And that's because physics don't change, so the re-entry aerodynamics are the same regardless of what decade it is.
Yeah.
And then there's the service module, which is really a barrel structure on the back end with 4 solar arrays hanging off the sides. So that's the real heart of Orion that does the mission in deep space.
Okay, yeah, I'm imagining a capsule with a barrel attached to it now.
That's
But definitely, I mean, if you honestly, if you're listening and you don't know what it looks like, definitely look it up. It's pretty cool. And you have a lot of different models of Orion, right? Because there's there's the one that's going to fly, but then you're using a bunch of different ones for testing, right?
Yeah, of course. So everything we do, we have to test before we fly it.
Sure.
So we go through a whole bunch of different pieces, right? So we built a structural test article, which they do vibration testing and acoustic testing on, and they put loads on it to make sure there's no stresses that we weren't calculating, because you have to prove that the structure we built is strong enough to survive. So
right.
You have to validate all of the analysis and design you did. And then there's ones we use for drop tests. There's flight test versions. There's ones we drop in the ocean that the crew gets out of. There's a mock-up in Building 9 here at JSC, which is the interior is all accurate so that the astronauts could be trained in there.
Yeah.
And the designers can see where things lay out, because it's a lot different being there and putting your hands on it than it is to just have a CAD model on a computer screen.
Definitely.
So you got to make sure your vent doesn't go where your hand controller is and stuff like that.
Yeah.
So
And that
we have lots of different versions of Orion, really.
And I feel like that one, the mock-up version, would be good just for ergonomics, right? Just see where things are pointed, and you're right. You can do a computer simulation, but once you sit down a human in there, you really can find a lot of stuff out, right?
And we really do. The astronauts
Yeah.
come in and do testing with us. We put a suit on them, they get in the seats, and then they actually tell us where the hand controller needs to be so they can reach it while they're seated during launch. Because, you could calculate the length of someone's arm, but you don't really know how comfortable that is for a variety of people.
Right.
So the point of having a mock-up is the astronauts themselves get to have input on the design for where things go.
Okay, so honing in on that just a little bit, I mean, that's just because it's a NASA Johnson Space Center thing. We have a facility here, Building 9, right, the Space Vehicle Mock-Up Facility. And we have something very similar on the International Space Station, right? Mock-ups of, one-to-one scale versions of what you would find on the International Space Station, but it kind of gives you a lay of the land in a way.
Yeah, it's the same concept been used for decades, and Building 9 it sort of evolves with the programs. I mean, I think they did Apollo work in it way back in the day, and then it had a space shuttle, and now it has ISS and Orion and the commercial crew vehicles all in there. So it's kind of a cool facility. It's like a playground for spaceships. But that's where the astronauts and everyone can get in and really see what's going on.
Yeah, and so for Orion, that's a lot of different types, and they all serve a different purpose. So is there so many because there's just different things that you have to pay attention to? Are you doing multiple tests in different locations? Like, what's the logic behind having so many test articles?
Well, the different test articles are really built for that specific function, right?
I see.
We don't need to build a complete Orion. That would be very expensive. So you build one that's structurally accurate, and you go do all the structures testing on it. But you don't mount all the avionics and computers and things like that in it. They don't need to be there for that kind of testing.
Exactly.
And then when we build the one in Building 9, we don't really build the right shell because that's really expensive. So you build basically a plastic, and we use 3D printed parts to represent that shell, but you really want the inside to be accurate, and it doesn't have to be functional, but you need the box the right shape, for example. So we use different ones because first off, you need to do a lot of that testing in parallel. We can't just build one and have it move from facility to facility, but you build each mock-up or test article so it's purpose for that, and we can have a lot of things going on at once, and there is a lot of things going on at once.
Sounds like it. Absolutely. So I mean, is there a version right now that exists that has all the different parts together?
No, but we're building the real Exploration Mission 1 Orion is already under construction at the Operations and Checkout building at the Kennedy Space Center.
All right.
So the real Orion crew module is already there, and I think part of the crew module adapter is there. So they're actually starting to put the real pieces together, and that the only complete vehicle will be the one you fly.
All right, yeah. So that one's going to be for, I mean, it's another test, but really it's complete, right? So EM1, I mean, we can skip around. I know we have like kind of a model of how we want to have this go, but I mean, EM1, what is that? That's another flight test, right?
Yeah, so Exploration Mission 1 really kind of is the ultimate flight test. It has everything but the people. And some of the equipment the crew needs, right? We're not putting the complete life support system on because the crew isn't on there.
Sure.
But the rest of the vehicle, for all intents and purposes, is complete. So that is the ultimate flight test. So, right, even though we're doing all this testing on the ground, we've still got one giant test to do in space because things don't always work in space like they do on the ground. So we do have to really finish the testing in space before we put crew on. So Exploration Mission 1 is that first uncrewed flight test before we give it the thumbs up to put people on.
There you go. And you have all the different tests that coming together, right? So you have all that vibration testing, the structural test, all the ones you were hinting at, the interior, whatever, all jam-packed into this one, everything works, here it is, mission. So except the people, obviously.
Right.
So
yeah. So and it's a model used across all sorts of programs, right? Aerospace industry, other spacecraft. Everyone has to do testing before you're ready to put people on something.
Yeah. Okay. And the mission profile, we can get into it later in the podcast too, but the mission profile of that is what? Where's it going to go?
So we're intending to send Exploration Mission 1 out to the moon, in what's called a distant retrograde orbit. So distant meaning we're really high up from the moon, so a high altitude orbit around the moon.
Oh, okay.
And retrograde means you actually orbit opposite the direction the moon is going. So if you looked at the moon from the North Pole of Earth, it's moving counterclockwise. And our orbit around the moon is moving clockwise.
Yep.
So that's the retrograde. So that's a distant retrograde orbit. It's a very stable orbit. It doesn't require a lot of propulsion to get into and out of. And so that's why we're just using it. It's a good stand-in to do testing and have a steady state condition to make sure we're testing everything out. So that's our destination, but the whole mission should be between 26 and 42 days long. So we have lots of time to test things out. And then when we come back to Earth, we're going to do a 25,000 mile per hour reentry and do the entire entry with all the heat shield and everything that you need to confirm it's working. And all our models were right before the crew flies.
Oh, wow. Okay, so, I mean, I'm thinking when you were talking about that mission profile, the one that came to mind was Apollo 8. That one had people on it, right?
It did.
But it went around the moon and then came back, but it didn't land on the moon.
Right. Apollo 8 didn't land on the moon. So all of the Apollo missions, they had a very defined target, land on the moon. So
Obviously,
if you go back through all the Apollo missions that led up to it, each one achieved another objective toward the moon landing.
Yeah, all stepping stones.
And Apollo 8 was the first demonstration of actually sending a vehicle from Earth to the moon and proving that could be done.
Right.
So it had people on board. They
Yeah.
didn't have as much advanced computers and communications that we have now. So they
Right.
could not have achieved that mission without people on board.
Oh, yeah.
We can now with computers. So that's why we can do this as an uncrewed demonstration before we put people on.
Okay, so is it similar? Is it like I don't know the exact details, but did Apollo 8 also do a retrograde orbit?
So Apollo 8, yes, it was retrograde, but
Okay.
they did go down to a low lunar orbit. So they were within 100 kilometers of the surface.
Yeah.
And we'll fly by at 100 kilometers from the surface just when we're doing a powered flyby, but we're not going into a low orbit like that.
So this is a bigger. It's kind of elliptical too, right? It's going to go way out past the moon.
Yeah, it's 70,000 kilometers on the far side of the moon. So
Yeah.
we're way past where any of the Apollo missions went.
Right.
And that's because we're working towards a gateway architecture in the future of, a staging ground for development of Mars missions and things like that. So it's a different purpose than actually an objective to land on the moon.
But it's kind of the same thing in Apollo 8, where before you can land on the moon, before you can get to your deep space, your objective, you need to make sure that everything works first. So it's just it's another test.
Yeah, and Apollo had multiple flights in low Earth orbit before they even ended Apollo 8. So they had several uncrewed flights, and then Apollo 7 was actually the first crewed flight, and it stayed in low Earth orbit before Apollo 8. So they got to have lots of test flights. And so we're relying on a little bit leaner of a test flight strategy because we can do more ground testing now.
Yeah, and like you said, we have the technology where we can collect the data we need without, so...
Yeah, so I mean, Apollo's computers were something like, less power than those old calculator watches, right?
Right.
So there was only so much they could do. They really invented computers and microprocessors and stuff like that weren't really around yet. So now we've got super advanced computers. We can automate a lot of stuff in software that you could have never done in the Apollo days. So we are actually automating a lot of the vehicle and software so that critical actions like burns can be done without ground intervention.
Oh.
Because some of those burns happen on the far side of the moon where you have no contact with Earth.
Right.
So we've got to be able to have that software on board the vehicle, whereas for Apollo, those were literally manually conducted burns where the astronauts were triggering the engines and stuff.
Right.
So, I mean, that's one example of why we can do that without people now, and they could not have done that on Apollo.
Yeah, exactly. So, I mean, going back to Orion, we started talking about the whole overall view of it and kind of how it's structured and shaped. Let's, kind of go inside for a second. How many people can go in Orion?
So we can take up to 4 people. That's what our design is for.
Okay.
But Apollo did 3. But we've got way more room still inside for the crew because with the advances in structure, right? So we can use carbon fiber structure, and our computers are obviously much smaller than they were in the 60s. So space-wise, the crew has a lot of room to move around. You can actually stand full height if you're standing on the back plane where the lockers are in the docking tunnel. So you can stand up in Orion.
Wow.
And in Apollo, you really only sort of had 3 beds or chairs where they got into when they launched, and your space was basically arm's reach between your back and the control panel. So
tight squeeze.
We've got a little bit more comfortable of a ride for the crew, but it'll still be a long haul on a long mission.
Is that the logic behind the design too? Is it for comfort, or is there other stuff that you're trying to put in there? Because now you have smaller computers, more space, more people. What else? What's the logic behind it?
It's not so much comfort, but to support a little bit longer mission. So we should be able to do 21 days, 4 crew for 21 days in just Orion.
Wow.
So when you think about how much food and clothing and personal hygiene space you need,
for
stuff
21
like
days,
that, there's actually rules that NASA has about how much volume per crew member you need. So we're meeting those requirements. So for a 3-week mission, you need a little bit more volume if that's the only space you have to move around in. So we're meeting those requirements. It's not like we're designing for comfort. We're designing to achieve exploration goals and making sure humans are comfortable and can achieve the mission safely.
I think having a lot of space, a little extra leg room, and enough food for the whole mission, I think is pretty much, that's all comfort stuff.
Kind of important to be able to eat.
Kinda, yeah. Okay, so we're talking about 21-day missions. We're talking about going outside the moon. Can this be a low Earth orbit vehicle, or is that not part of the vehicle? Like, can it go to the International Space Station?
So when Orion was first conceived, it was supposed to be able to do both,
Oh, okay.
ISS and lunar orbit. But we've since moved on past that. We are now trying to do the commercial crew program to really go to ISS.
Yeah.
And it's really kind of having vehicles designed for different purposes, right?
Mm-hmm.
You can drive to work in your giant 4x4 pickup with a camper and stuff like that. And that's like Orion, right?
Right.
Big camping trip, lots of supplies, things like that. You could go to the ISS in it, but it's not a good use of the vehicle, right? We're trying to do the exploration objectives. We've got a lot more stuff and a lot more capability, and it's better to use it for exploration. And then the commercial crew can design for the specific vehicle. It's like your Civic you drive to work in. You know, you only need a car to get to the space station. You need a big truck with all your camping supplies to do exploration. So there's really a purpose difference. So yes, you could go to ISS with it, but that's not really what we're trying to do.
I love that analogy, by the way. I mean, as much as I would love to take a Class A trailer to work every day, but that would be pretty awesome. It would be a total waste of time and money and resources.
It's a little bit of overkill for the mission you're trying to do.
Exactly. That's a perfect way of describing it. So, I mean, you're talking about an RV, a camper, pretty much, but a space version that's going to go way out. So you're going to be going on these big space camping trips. You need a lot of food and stuff. Is it going to be similar to International Space Station food, or are you designing a sort of I don't know how to describe it, but is it going to be different from International Space Station, or are you taking some of those lessons?
I think they're using a lot of the same foods from the space station. I mean, the crew, they've done a lot of testing on what they get at space station. Now, for Orion, we're a lot more space constrained and mass constrained, because whatever we put on, every pound you put on the vehicle, you got to send that to the moon. So that's more prop, more resources, more space. So
Right.
I think they've done a lot more advanced work on energy bars, basically. So compact, there's like 700 or 800 calories in a bar.
Wow.
That's a whole meal replacement. Now I can fit that in Orion, so at least once a day I think they'll have these energy bars versus a whole meal with the freeze-dried food they'll still have, but we are trying to condense down a little bit of what we can take because we have to fit it in a smaller vehicle.
Oh, okay. Yeah.
So, but the food sciences are still doing a lot of work, and we're building off of what ISS had.
Yeah, but I mean, it's that whole idea of mass is money. So you got a certain amount of weight that you have to plan for. So you got to make sure that their meals are really tiny and don't take up a lot of space, but are jam-packed full of calories and can really meet those caloric needs that the astronauts need.
Yeah, and getting out of low Earth orbit and getting to the moon, I think you need like 10 times the amount of prop to do that, right? You need so much prep to get a low Earth orbit, and then you need like 10 times that amount to leave low Earth orbit. So it has a multiplying effect for every pound you add. So 1 pound getting it to ISS is easy, quote unquote, but you need that much more for every pound you send to the moon.
Right. So. Yeah, I like that quote unquote, because going to space is not an easy thing. But
absolutely not.
Now you're planning for things that have this tenfold factor. So it's pretty crazy. So, I mean, what about, going back inside? You said they have plenty of room to sleep and stuff. What about, is exercise a concern? Because I know exercise, they have to do it almost, 2.5 hours a day on the space station. Are they going to have something similar for these 21-day missions? So
we do have to fit in an exercise device. We're really trying to get them to give us a very compact exercise device, because you've got room, but you're going to be trying to do exercise with 3 people around you in a small cabin. Trying to do a pull-up, and you'd be smacking your co-crew member in the face, right? So we're trying to work on a compact exercise device, and they have ways to do that. You really need a lot of exercise equipment when you're doing long duration missions like on ISS. So 6 months, they've got the treadmill, they've got this thing called the RED or iRed, which is like a weightlifting device. So when you're doing long missions, you need a lot of exercise equipment. That stuff doesn't fit in Orion.
Yeah.
You need some short-term, smaller, compact exercise equipment in Orion, and then if you build a gateway around the moon, kind of like a little mini station, then you need to put your big exercise equipment on that for a longer mission.
Okay.
So we've all got to sort of do our part and our piece. So.
Yeah. So, I mean, 21 days is a little bit short of a mission. I know that they have these exercise requirements on the International Space Station because there's some certain things that happen in the body over a 6-month time. Is there things that you know of that happens to the body in a 21-day time? And I'm sure you're planning for that in your exercise equipment, but, what does that look like for the human body in space?
Yeah, so I know from the surgeons and the medical doctors, they see a degradation in the human bodies even over just 2 to 3 weeks.
Oh, wow.
So even over a short time frame, like say the shuttle flights, same thing. The crew was still doing exercise even though the mission was only a couple weeks long, so they didn't come back deconditioned. With muscle loss and things like that.
Yeah.
So we've still got to do that. So the UC deconditioning in the human body within, a week of being in orbit. So you can't let it go and ignore it, but we don't have to do as much as a 6-month mission.
Right. So. Yeah. I mean, so you talked about it being sort of like a space camper, space RV. That's a great way to describe a vehicle that's meant for, like you said, the mission, for going out into deep space. What else about Orion makes it a good vehicle for those type of missions, for deep space missions?
So one of the things with Orion, it's very hard to do, but we're trying to, is to make it capable of a lot of different orbits. Or destinations or mission timelines, right? So we need to be able to handle the DRO. We're looking at other kinds of orbits. So whatever crops up in the future, Orion can support. So we're trying to build in some flexibility. And then the other key piece of Orion is to be able to abort and come home. So if you have a problem, we need to turn around and get the crew back and do that within a few days. When you come back from the space station, if there was an emergency, it's a matter of hours. It's like 1 to 3 hours and you can be on the ground. So it's not like a true emergency, you've got to have tons of supplies. But the fastest you can get home from the moon is 3 to 5 days.
Okay.
So you have to have, in an emergency, still have the supplies on board, the vehicle capable of, if you, say, lose an oxygen tank, you've got to have another one to survive the multiple-day trip home. So that's the kind of challenges is, we need to be able to get out there, and then we also need to be able to safely come home.
Wow. So it's redundancy, but then, you already hinted at before that, mass is money. So, and you only have a certain amount of mass. Now you have to build in these redundancies. Now the things that you can put on the vehicle are restricted. I can see how this can really spiral all these challenges.
It is. It's a big snowball effect.
Right.
It's how many emergencies do you protect for? What are all the different scenarios we can think of that you need to cover for? And then at some point you have to just realize there's risk.
Yeah.
Well, it's a risky thing to do to send people to the moon. And at some point you have to draw the line and say, okay, these are the risks that we have to take to do this at all.
Yeah. You have to accept the risk because you're right. This is new. That's the whole part of exploring, right? Is you're trying to fit, there's only so much you can just plan for because you have to be in discovery mode too.
Right.
So, yeah.
So we try to build in redundancies to cover for a variety of causes.
Yeah.
But at some point you're done. You can't put 5 oxygen tanks on board just in case, right?
Yeah.
We've got to make sure we know what we're designing for and try to cover the situations we can plan for.
Yeah. So you hinted at before that it's comparable to the Apollo capsule. So how is it similar? How is it different?
So similar, the shape. Obviously,
Yeah.
you can look at it. You draw a lot from those lessons learned on Apollo. The shape of the capsule is the same. We both have the service module. But then we've had a lot of advances in the structures and the computers and things like that. And then a few other things. Apollo used fuel cells, had a very short mission lifetime possible. As a result, we're using solar arrays, which will enable longer duration missions because once you go over a few weeks mission duration, the solar arrays will continue generating power. It's free energy from the sun.
Yeah.
So that's like another obvious difference in the two things. And then we're using things like we have it's called an encapsulated service module, where we put fairings on to protect those solar arrays during launch because of the aerodynamics of the wind that would rip them off.
Oh, yeah.
And so then we jettison the fairings on ascent. So Apollo didn't have that. Their service module was the external structure.
Right.
So there's a few other differences, right? We have a big launch abort tower on top. Apollo did as well. I think ours is we've designed it a little bit different. But all in all, it's still the shape is very much the same. And we can do longer, right? The 4 people, 21 days. Apollo was 3 crew for like 14, stuff like that. And then we're designed to be able to dock with other things. So when we start building out a habitat or something, you can be out there for months at a time.
Right.
So once you have another habitat, then Orion with its solar arrays can just hang on and wait throughout a longer mission. So we're trying to build in a multi-month capability in a quiescent state, so you can do long duration missions out near the moon, and that is not something Apollo could have done.
Yeah. See, I mean, if you were to just look at it, you'd be like, it's a big Apollo, but it's these little details that are really make
It's
or
all
break.
the details.
Yeah, for the mission. I mean, if you don't have this sort of, if it doesn't jettison this thing right, it's not going to work. If it doesn't have this much power, it's not going to work. Yeah. So it's all these details that really make or break the mission. And it looks like just the capsule flying through space, but there's like a million things that have to happen for it to work successfully.
Yeah, the change in what you're trying to do with it drives a lot of design decisions. I mean, that is the engineering process, is you give yourself a goal, and then all of a sudden you're down this rabbit trail of, well, if I want that, I have to do this differently. So the power system's a good example. If you want a long duration mission, you need arrays, which don't require consumables. Fuel cells require hydrogen to feed them, and so you can only do missions of however much hydrogen you have on board for your fuel cell. If you have arrays, well, now I can do long missions. So that drives all of your engineering design decisions when you make those sort of objectives.
Mm-hmm. So in the beginning, when we talked about what is Orion, you kind of described the shape of it, what it looks like, and then you said there's this barrel behind it. You said the service module. What role does that play in all of this?
So the service module is critical to Orion's deep space activity. So if you think about the crew module, that's got our computer. So that's the heart of the vehicle. It's the pressurized volume for the crew to stay in, and it's also the piece with the heat shield and the parachutes that land the crew safely. Mm-hmm. But on its own, it can only stay alive for a few hours because it's got the batteries, but that's only a couple hours worth of power in them. Mm-hmm. So with the service module, you have your main propulsion system. So that's how you're going to get home from the moon.
Right.
And how you're going to control your flight to get there. Kind of important. It has all of the crew consumables, the oxygen, nitrogen, and water tanks. So that's feeding the crew module for the crew while you're up there. It's got the radiators. So the crew, the avionics, computers generate a lot of heat. So we have to get rid of that because the crew needs a cabin that's comfortable. You can't have that 100 degrees.
Yeah.
That would be horrible to work in, right? So we have to air condition the cabin. We have to get rid of all of that heat. So it runs through ammonia pipes on the radiators to get rid of it. Mm-hmm. And then you've got your power, you've got your big or solar arrays out there. So there's all a sort of your main functions for your vehicle are built into the service module, and a lot of those come from the European Space Agency.
Right.
So we're partners with the Europeans. They're building a huge part of Orion, and a very critical part, right? We can't fly without the European Space Agency's part of the service module.
Yeah, absolutely. Because this is, I mean, is it fair to say deep space exploration is a multinational, international objective, and we're all kind of pulling our resources together to make it happen in a way?
Yeah, I mean, I think we've had great partnerships. We've learned all the way from Apollo-Soyuz to the International Space Station, and now looking to the future, we all kind of have this model of trying to work together because this is very hard, it's very expensive, and ultimately it benefits all humanity.
Yes.
So being partnership in doing it is very much a key part of NASA's plans.
Yeah, because all of these different things that we're learning along the way to meet this goal, we're kind of inventing technologies, right? I know just James Webb invented a couple different technologies in order to make James Webb be James Webb. But, you have to come up with something and solve problems that you wouldn't otherwise solve in other situations, but can be applied other places.
Yeah, I mean, and one of the key ones going forward is when you're, say, going to Mars, you want a closed-loop life support system.
Yeah.
You want to recycle all the water, and they're already doing this on the space station, and so that's a key technology that's being developed for future missions and stuff.
Right.
So closed-loop life control, but now if you can preserve water, that could be a key technology on Earth for a water-starved region. So if you can improve on that technology, there's the opportunity to improve things on Earth because we've solved problems in space.
Yeah.
And engineers really need a challenge to figure out how to solve problems, and there's a good one for people to work on.
Now, going back to Apollo, I know for them, they brought all the water that they needed on their couple-day mission to the moon and back. Is Orion going to have a recycling water process, or is it going to bring water?
So Orion is, we're not closed loop. So we're an open loop system. We're bringing all the water you need for the 21 days. That includes hygiene, that includes drinking water and rehydrating the food they're eating.
Okay,
So all of those things, we're bringing the tanks full of water because we're designed for that 21 days of crew support.
Right.
When you're looking at a long duration around the moon and a habitat you put at the moon for a long duration, that habitat absolutely needs some closed loop life control on.
Absolutely, yeah. So that's where we'll probably see the next generation of closed loop life support systems. That. So and it's closed loop because water's a part of it, but then also I know environmental control, right? Like oxygen, that's part of it too, right?
Right. So oxygen, a lot of that, especially like say if you're trying to do EVAs, you want to save that air. You don't want to dump it overboard when you're doing EVAs. So there's a lot of technologies that have been improved on the space station and continue to be approved in a lunar environment to continue enabling longer, even more and more ambitious space exploration in the future.
Absolutely. So let's kind of go back inside the Orion and see and kind of point out the different features, what's cool, what's upgraded, and what kind of technologies are being brought to the table. I know you said there's a lot of space, but the computers are smaller, right? So is it, what kind of computers do you have on Orion?
So we're using Honeywell computers, and I actually think they're the same types used on Boeing 787 aircraft. So
cool.
These are avionics, high technology avionics, more state-of-the-art, and we're running, there's 4 computers, and they actually all run in parallel, because if one fails, you don't want the spacecraft to go, I don't know what to do. So all 4 of them run in parallel, and we do that for a lot of reasons. Number one, time critical things. If one goes down, you have 3 others already working, and they're checking each other to make sure if one has an interrupt and produces bad data, you don't use it.
Yeah.
So all of them are running in parallel on the same data and checking each other to make sure it's all right.
Cool.
And then there's other things. There's lots of radiation in space. So computers and avionics don't like radiation. They get hardened to protect them, but you can get single event upsets, which basically changes a bit from a 0 to a 1. Well, you change a bit from a 0 to a 1, and you get a completely different answer in the algorithm.
Oh, no.
So we put 4 on there to protect for the likelihood of, 2 even getting interrupts. Near, because you can get 1 with an interrupt and then very shortly after have another one. So, we run 4 because we've done the risk calculations, and we think with 4, we've, bought down that risk as much as you can do without, you could put 100 computers on there, but it's still technically possible to have them all go down at once.
Yeah.
Right? You can never completely get rid of the risk. So,
do you have some sort of radiation protection technology kind of built into Orion?
So the avionics are called rad-hard, radiation hardened, to protect them.
Cool.
But the important part is the crew.
Obviously, yeah.
So most of the time, they're getting, background radiation. And when you're outside the magnetosphere of the Earth, they're getting much higher doses of radiation. A few weeks in space at the moon is equivalent to 6 months on the ISS. So you see a lot of big radiation differences because you have to actually transit the Van Allen radiation belts to get to the moon.
Right.
But then you have your big worries are solar flares from the sun, which send a huge amount of radiation over a short period of time. Mm-hmm. So if that happens, they actually have shelter procedures in place where they'll empty out the lockers inside Orion. The crew will get down in those lockers and put as much stuff around them as you can. So all of their clothes or bags of water or whatever will get packed around them so that you basically create a little habitat, a little shelter in the middle of Orion, because the more stuff, the more structure you can put between you and the outside, the less radiation will get through in those events.
Right.
So we actually have procedures. They have to demonstrate that it works. They just recently did that testing actually in Building 9.
Oh, cool.
In our mock-up. So that's one example of how the testing happened. So they can actually shove the crew. They had to make sure you could fit the crew.
Yeah.
They can be semi-comfortable for, whatever length of time is required, and have their computer to keep working and stuff like that, and commanding the vehicle in there and stuff like that. So they've, we have to protect the crew. So that's another thing we can do is you literally just put them in a little pocket. They build a little fort and hang out while a solar particle event is going on.
Yeah. So how about those events? Obviously, you're planning for it. It's part of your mission. You just did a test for it. What is the procedure for, how long do you have from when you detect it to when you communicate it to the crew and they have to get into this mode? And then, how long do the events last and they have to stay there?
So, the good or the bad thing, right? So when the sun has a solar particle event, you see the solar flare, the light, so that travels at light speed. So it's, seconds or minutes from the time the event happens on the sun till we see it
Yeah.
on Earth, but the actual particles travel much slower. So you have a day or two before the particles get to the Earth-Moon system.
Oh, that's a decent amount of time.
Yeah, so you can see this happen, and we have satellites that are detecting that. Same thing they use for the space station to detect when some of these things are happening.
Yeah.
So you see the event happening, and you have a day or two to prepare the crew or get in their habitat and stuff. And I think it's about a day long where these particles can be passing through.
Wow.
So, that's the type of, you get an advance warning, and then you have, about a day they're going to be hanging out in their little shelter until the levels have decreased enough to get back out again.
Right. I wouldn't have thought of that. Just, if you can detect it in a few minutes, then, I would think, oh man, they have no time to prepare for this. But I feel like that's a way better situation. And especially you have the procedures to kind of go through that too.
Yeah, luckily we're far enough from the sun that we have that sort of advance warning time.
Yeah.
And it's not as hot.
Definitely. So, when I imagine the future of space technology, I'm imagining a futuristic, like Interstellar or something kind of movie with all kinds of fancy technologies. I know, talking with some folks, touchscreens were considered, I guess, but there's some challenges with touchscreens. Is Orion using something like that, or is the challenges too much and they're using something else?
So we're not using touchscreens.
Okay.
That was, I think, a trade early on in the design. The crew had a lot of input in it, but I think one of the reasons not to do it is because, especially when there's a lot of dynamic motion going on,
Yeah.
you're trying to, you're suited, you've got a glove on, you're trying to push a button on a screen, but your hand's shaking because there's a lot of vibration. So I think that was one of the leading factors to decide not to.
Right.
So we're using computer screens, and they've got edge switches. So there's actually physical buttons around the outside of the screen, similar to what you can find in airplane cockpits.
Okay.
So we can change the software, so it'll put data beside it, and you can say, so for one screen the button might do this, so they have commands they can input with those buttons, but it's actually a physical button they push, so that way you're getting the right input versus a shaky hand trying to hit a touchscreen button.
Yeah.
So that was one of the big challenges that was decided early. So we have edge switches and little swizzles, so little toggles, so they can move the cursor around on the screen.
Oh, wow.
So it's a little bit more tactical feedback, so especially in a vibrating environment, they can control the computer a little bit more precisely.
Have you tested like that, something like that, where you put them in an environment where they're vibrating, as if they were in a launch or some other kind of event during the mission, and you need to be pressing buttons in certain cues?
I think that's actually been done already. So our mock-up in Building 9, the screens work.
Cool.
So those are already working. They can test out. They have a whole team doing the displays for the crew. So it's very important to make sure they have the right information on the screen, all the information they need to make decisions, and then have all the commands in a procedure format so they can very, without having to think about it, follow what needs to be done. Because in an emergency, you don't have time to flip through a bunch of screens to find the button and commands you want.
Got to be fast, right?
So they've got it all. They've got a whole team building the displays. I think they've actually put the crew on a shaker table and had them do this, but if they haven't, they will be. But making sure that the crew can execute the procedures and have the right displays in front of them to know what to do is a very important part of the vehicle design.
Right. Yeah, you wouldn't be thinking about that if you weren't if you were just like, oh, just put touch screens on Orion, and it's just like, no, there's a lot of challenges. They're going to be vibrating. They have to make sure the buttons work.
So that's what the engineers do, is have to think through all the problems and get the input of the crew and make sure we're putting through not the best solution ever, but an acceptable solution that meets all of the competing needs, right? Touch screens may be nice in some situations, but in others not so much. So what's the acceptable solution that balances all of those factors? Right.
So I know when it comes to Orion, one of the big challenges just of the mission itself is that it's a fairly large spacecraft, right? It's bigger than Apollo, and it's going to go so far out that when it comes back to Earth, it's going to be coming in pretty hot, right? It's going to be coming fast. So one of the big technologies for this whole thing is a heat shield, right?
Yeah, so we're coming in, when you return from the Earth-Moon system, it's not just Orion, it's any spacecraft you send out to the moon.
Okay.
We'll come back and you'll hit entry interface when you actually hit the atmosphere of the Earth, or not hit, but gently enter the atmosphere of the Earth.
Yes.
You're going around 25,000 miles per hour, which is 11 kilometers per second. So
pretty
you're
fast.
really cruising.
Yeah.
And so when you do that, it's actually the atmosphere is helping you because we're using the atmosphere to slow down.
Okay.
So we use that blunt capsule shape as aero braking. So we're letting the air slow us down, but in doing that, it's creating heat.
Yeah.
So all of that friction, basically, and the shock wave of that, you're turning the air into plasma.
Oh.
And so the plasma you're creating is incredibly hot.
Yeah.
So our heat shield can get up to around 5,000 degrees Fahrenheit.
Oh, man.
So we're talking a lot of heat. So on Orion, we're using Avcoat, which is the same material Apollo used. So again, there's another similarity.
Cool.
But that's like really the only use for Avcoat. So after Apollo, they didn't manufacture it, and a company called Textron makes it.
Yeah.
So they had to go figure out how to make it again for Orion. So we're using an Avcoat heat shield like Apollo. One of the mods or modifications we've done for Exploration Mission 1 is we're actually using a block application system. So it's like big bricks of a heat shield that have been patched together versus what's called a monolith where you make it all out of one piece.
Yeah.
And we had reasons for doing that, thermal stresses and stuff like that. But that's one of the big things we're testing out on Exploration Mission 1 is the new design of the heat shield, which is a block system. So if you look at it, it looks like a bunch of bricks that have been put together on our heat shield.
Yeah, instead of one solid piece.
Right.
Is it kind of the same logic as the shuttle? Because shuttle also had the little, is it tiles or blocks? And
Yeah.
the whole concept was if one of them's not good, you just take it up and pop in another one.
So
Is it-
we don't reuse ours. So
Oh, okay.
the concept of the blocks is because when it gets cold in space, it actually creates a stress and could crack it.
Oh.
So one of the reasons is actually going to the block is so that we are more safe after it's been exposed in space, that we don't develop cracks that weren't there before we launched.
Right.
So that's one of the reasons we went to the block. You mentioned the shuttle tiles. So we actually used the same thing as the shuttle.
Oh, cool.
So the shuttle had tiles on its belly.
Yeah.
But those can only get up to around 2,000 degrees Fahrenheit.
Yeah. you need
So we're
5,000.
using those on the back shell. So the conic part of the vehicle is covered in the same tiles like the space shuttle were.
Oh, wow.
And then we've got a tape over them so you won't really see them.
Yeah.
But yeah, so we're using the same tile material, ceramic tiles that the shuttle had on the back shell, but they're not enough heat rejection or heat protection to use on the heat shield. So we have to use the Avcoat on the heat shield like Apollo did.
Yeah, because there's that much of a temperature difference, right? Like that's getting your, like you said, the brunt force. So that's your 5,000 degrees. But on the other side, you don't have to worry about.
Yeah, so they're
that as much.
basically, the back shell is in the leeward side. So it's
Yeah.
protected. The heat's sort of going around it. So it doesn't get nearly as hot as the heat shield does.
Wow.
But they're a lot lighter. So once again, the reason you use the two different things is because we're trying to save mass. So on the
Yes.
back shell, we can use the tiles. The ceramic tiles are super light. It's kind of amazing how light those things are.
Yeah.
So we cover the back shell in those, but we have Avcoat's a lot heavier, so we use that on the heat shield.
Oh, okay.
But the heat shield itself is only about 2 inches thick. So we're doing a lot in 2 inches on that Avcoat.
Yeah, that is some strong stuff
Yeah.
for 2 inches. Yeah, you're not no layers peeling away there, right? 'Cause you
Actually,
don't
it
really-
does. Avcoat is
Really?
ablative, so the way you reject the heat is it burns away as you're re-entering.
Whoa.
So we're going to lose about half an inch worth of Avcoat as you re-enter. You have to have enough there that we've protected for how much could burn away
Yeah.
and still have protection and things like that. But the Avcoat does get thinner as you're coming in through entry.
Yeah. Is it sort of a one and done kind of technology then? Is it like you use the heat shield and then, okay, that's good for that mission, take it off, put it on a new heat shield?
Yeah, the heat shield absolutely is not reusable.
Yeah,
So we're not going to try to reuse that, especially now you've dunked it in the ocean.
Yeah.
So a lot of things don't like salt water.
Yeah.
So you won't want to reuse the heat shield.
Right.
It had its day. And you build a new one.
Right, and it's been through some stuff, so let it just let it go. Put on a new one. We'll deal with it later. There's a lot of other good technologies on there too. I mean, is there anything like even the seats that you're revisiting, or are you doing something different there?
So the seats are our new design. Apollo used actually these sort of canvas beds to save mass. We're using aluminum structure,
Okay.
thinned out and stuff, but they're adjustables for different size people.
Cool.
Right? So you can fit all the way from like a 5th percentile woman to a 95th percentile male. So
All
you can
right.
fit quite the range of people inside the vehicle.
Yeah.
But the seats are aluminum for launch. They've got leg rests and stuff. The crew, like everything, you launch on your back. So you're taking the G-forces in the chest to Vassant. But then you can move the leg panels and stuff like that after you get on orbit to give yourself more room, so you don't have these foot panels sticking up in the space. So the seats are a new design, but there's nothing revolutionary about them.
They're just, I mean, it just sounds like it's built to be flexible for different sizes and to be as comfortable as possible. So
Yeah.
when you're launching and you're having a lot of G-forces on your chest, you're at least, you're going to be in good shape pretty
Right.
much. Yeah, you're not going to be tossing and turning all over the place. So they're going to be, are they going to be wearing what's the suit they're going to be wearing? Is it kind of like an orange pumpkin suit that they used to have on shuttle?
It is kind of like the orange pumpkin
All right,
suit. I
cool.
mean, I think the acronym is MACES. Don't ask
MACES.
me what they stand for. It's an upgrade from what they had on shuttle.
Cool.
But it is very similar. So they'll be in the orange little pumpkin suits for ascent and entry,
Right.
with gloves and helmets. So if something happens, because we can abort at any time during ascent, and you
Oh.
land in the ocean. So on ascent, you land in the Atlantic Ocean, and when we re-enter, we land in the Pacific Ocean. So the suits are there for their protection,
Yeah.
especially after they land. So if they had, say, something happened and they had to get out of the cabin, you've got that full survival suit thing
Right.
with the built-in, I think it's got the inflatable raft, like a life vest in it, stuff
Yeah.
like that. So so the suits are for their protection in case anything goes wrong.
They have a bunch of supplies just to keep kind of survive for a little bit, just in case something happens. I know.
The like signal flashing lights
Right.
for rescue crews to see them.
Yeah, a lot of it's like emergency stuff. Cool. Yeah, upgraded pumpkin suits, and it's a long mission, right? You're talking about 20-something days, so they get to take it off after launch, and I guess before re-entry they don't have it on, right?
They put it back on for re-entry.
Right, they put it back
Yeah.
on, but during that whole time they
Yeah,
they
so
don't
they'll
have
put
it
the
on.
suits on for ascent, and then after we've done TLI, the translunar injection burn, they'll be able to take them off. And once they get to orbit, they can take the helmet and gloves off, because once you've shown that the cabin isn't leaking air, they can make themselves a little bit more comfortable.
Right.
But there's not a whole lot of time until the TLI burn, so they'll probably still be in their suits while we actually do the burn, and then
Yeah.
once we've done that, they'll have time to actually get out of the suit, which takes a little bit of time to wrestle your way out of.
Yeah.
But then for the most part, they'll just stow them, and they won't get them back out unless there's a leak or we're back to re-entry, and they'll put them on for re-entry.
How about that? Yeah, that's all you really need it for, right? Launch and entry, launch and re-entry, I guess. So yeah, you're good.
Yeah, so we have a shirt sleeve environment in the cabin, so they'll get to wear your NASA polo shirt and pants just like every other crew.
Very cool. Yeah, I know. I think it's the International Space Station is at 72 degrees. I think is what they try to keep it at. I'm guessing will Orion kind of be the same?
Yeah, we'll be about the same.
Yeah.
And then we have fans and stuff to keep them cool. When they're doing exercise, we'll flip on an extra fan to make sure we're circulating that air better and stuff like that.
Maybe
so.
some air fresheners too.
I don't have any air freshener, so it's going to be you get used to your own smell though, right?
Oh yeah. Oh wow. Okay, so that's pretty good overview of the inside of Orion. And and when we first started, we were talking about a lot of the tests that they were going on, and we have different articles for all of these different tests. Just one of the big ones that I think we should talk about is one that we've already done, and that's EFT1, right? So what was that mission all about?
Yeah, so EFT1, which I got to be a part of and was awesome.
Yeah.
So technically, we mentioned Exploration Mission 1 earlier and talked about that being our first big in-space test, but it's actually our second. So Exploration Flight Test 1 was the first test we did in December of 2014, and that one was a test for the crew module and re-entry and the parachute system. So we actually launched the crew module, which was mostly complete, and just a structural service module, and it launched on a Delta IV Heavy, so it's a commercial rocket. We just put it on there to test it out, and it flew up. We did one orbit in low Earth orbit, and then we used the Delta IV Heavy upper stage to take us as high as it possibly could. We used all the performance that rocket had, so we actually only got up to 3,600 miles in altitude. But what that did is we were able to come back down at 20,000 miles per hour. So we got as fast an entry as we could, and that was to test the heat shield.
Yeah.
Because we've done a lot of analysis and things like that, but until you can actually test and validate that your models were right, you're guessing to some extent.
Right.
And then we did a full parachute test on that too. So basically we were able to test the ascent features. We built the crew module for the first time, and you learn a lot just by doing it.
Yeah.
So building that the first time was a lot of lessons learned on how to make it actually better. And then we tested the full entry entry sequence. So that means the forward bay cover. We have 11 parachutes, so the forward bay cover came off. We had drogues, we had the main parachutes and touchdown and the recovery team. So EFT-1 was our first in-space flight test of the crew module, and it was pretty awesome. It worked like almost completely according to plan. There was only like one even minor anomaly. So we were really happy with the data we got back on that, and we were able to make a lot of improvements in the design as a result.
Wow. All right. So, what are some of the lessons that you learned? I mean, you talk about the heat shield and parachutes, and you said launching and that whole sequence too. So what are some of the things you learned?
So one of the really cool ones was, so in building it, we originally had like 35 metal parts that made up the pressure vessel, or 35 welds and a whole bunch of pieces that had to all go together. And between the EFT-1 and the EM-1 crew module, we have only 7 welds.
Whoa.
That's done. So decreasing the number of welds saves a lot of mass. That was like a couple 100 pounds of mass saved because
Whoa.
you're doing fewer welds and making bigger parts with fewer seams. So those kinds of production things help teach you a lot.
Yeah.
And then we were able to learn a lot, like the way some of the systems worked, like the crew module cooling system. We saw some really interesting data, and so they were able to update their models with that. The parachutes learned a lot. Because that was the first end-to-end flight test. They do a lot of drop tests, but you can only get certain conditions on those flights and stuff. This was the first time it was end-to-end. So the models could all be updated, and we know more. So a lot of times when we're doing these tests is you're validating the models, and then you can reduce the uncertainties that you had to apply. So things like the heat shield could maybe get thinner, and we could save some mass because now we know more about the environment, so you can shave off some of the uncertainties, and we can save a little bit of mass. So there's those kind of improvements are what we learned out of the flight test.
Wow. Is that where you said it was the heat shield's now 2 inches? Was it 2 inches on that flight, or did you learn that you can shave it off and now it's 2 inches?
So now it's 2 inches. I think it was about the same on that flight because we weren't coming in quite as fast.
Okay, right.
But that's where we could update the models and reduce some of the uncertainties in what we're doing. So it helps you in future designs.
Right, and you saved a lot of mass that way.
Yes.
That's pretty awesome. I can't believe there's 11 parachutes, and they come out in, it's not like, you're falling through the atmosphere and then boom, 11.
It's not just like the up balloon house where they all come out at once. No, no, it's a big sequence. So for the first 3 parachutes are very small, and they're what actually pull the forward bay cover off. So when we've launched, you've got a big composite forward bay cover that's protecting all those parachutes from space because you have to make sure they don't get too hot or too cold, and they're still there when you come home again.
Very important.
So the first 3 really pull that forward bay cover away.
Okay.
And then you put out 2 drogues, and the drogues are used when you're still going really fast. We come out at 24,000 feet of altitude over the ocean. So we wait until we're down. We've slowed down as much as we can in the atmosphere, and you actually start this sequence at 24,000 feet. So the forward bay cover comes off.
Yeah.
The 2 drogues come out, which are smaller, and you're using them to sort of stabilize and slow down a little bit more.
Right.
And those are fired with mortars, so it's basically like a cannon.
Cool.
That blows those a boom, and there they go. And then when you've slowed down enough from those, we actually cut them loose, and you throw out 3 pilots. So the pilots are actually really small parachutes, but they're pulling out these huge main parachutes. So the big orange and white parachutes you're used to seeing are actually pulled out by 3 small parachutes themselves. And then the bags come off and the big parachutes come out, and you have your 3 main parachutes, the orange and white ones we land on safely.
Yeah.
And those even have stages, because if you opened them up all at once, the forces would tear the parachute apart.
Right.
So they've actually got Kevlar rings in them, and so they open up only so much, and then when you've got enough force, you pyro pops those rings, and it gets one stage bigger, and then another one, and then they get fully open.
Whoa.
So you're still going fast enough that you've got to stage that parachute so you don't tear it apart while you're landing. So when you finally get them out, they could actually cover a football field, the 3 big parachutes that you've got.
Wow. But you're right. I mean, you're going so fast, you don't want to deploy those first thing, because you're right, they'll just tear apart.
Right.
So you got the atmosphere, that's your first sort of quote-unquote parachute, because it slows you down. And then the next parachutes bring out, just open it up so that more parachutes can come out. I just love how there's parachutes to bring out parachutes.
I know, that's
think
the best part.
That was my favorite. Oh,
So the drogues are small enough that they can be fired with the pyro
mortars.
charge and a mortar.
Yeah.
But the big parachutes, they actually use an autoclave to actually compress them down, but then there's still these huge bricks, basically, of parachute material. And I mean, this is nylon, so it's really lightweight. But when you've got so much of it, they end up with this heavy mass, and you can't. There's no amount of, we don't have a giant cannon. So those have their own parachute just to pull out the main parachutes.
That probably, just the parachute system in general, that's got to be a decent amount of weight for coming up and going down, too. So that takes out a big chunk of what you can use, right?
Right. So all these systems, so we have to take to the moon and back. So, every time you take it someplace new, that's mass you have to push around space.
Yeah.
And that takes more prop and more weight. So the amount, our most critical mass item is the crew module, because that's all the mass we have to land under those parachutes. So if the crew module got super heavy, then you'd need even bigger parachutes. So we have to control very tightly how much mass we put on everywhere.
Yeah. Wow. Okay. That's just, it's extremely important, right? What's the benefit of using parachutes versus just like what you see in the movies, just like a propulsion system that fires jets and lets you land on the ground or something like that?
That would be awesome. We don't have, you need a huge rocket, right? You needed a huge rocket to get off the ground, and you then need a huge rocket to slow down and do some sort of propulsive reentry.
Yeah, there's more weight.
Right. Shuttle did it with the, they did aerodynamic reentry where the atmosphere slowed you down, and then they had the lifting body, so they could actually control their flight and land on a runway.
Yeah, I like how you say lifting body and not wings.
With those stubby wings, they don't quite work.
They're not really
super
wings.
well, right?
Yeah, just from talking to astronaut pilots that actually flew the shuttle, they said it was like flying a brick. It really didn't fly. It was like barely a glide.
It's
but
like
it
a
did
graceful crash.
A graceful crash. But it landed on a huge runway and stuff like that too. So go ahead.
And the reason we don't put wings on Orion is that's so much mass we'd have to then take to the moon. So the wings, the lifting body to try and send that to the moon is heavier than the parachutes we're using to land with. So that's another trade you have to make. If you want to send a lifting body to the moon, well, now I need an even bigger rocket just to get it there. So you keep trimming things off, and parachutes weigh less than wings.
Oh, there you go. Okay. So, obviously there is a logic to it. It's just, as cool as it would be to just land like a Star Wars ship or something, there's, we're not there yet.
Well, and the Soyuz does use a retro rocket that is just because they land on land.
Right.
And they have a rocket strapped to the bottom of their heat shield, and at the last minute, it takes off that last bit of speed.
Yeah.
So you can land on the Earth without hurting the crew.
Right.
Since we are landing in the ocean, it's a design choice that's been made, right? We don't need the retro rocket, so we can land a little bit faster. We're still only going 20 miles an hour. So we went from 25,000 miles an hour to 20 miles per hour in 20 minutes. But then we splash down in the ocean, so we don't need the retro rocket like the Soyuz has.
Yeah. Okay. So the design choice of the ocean is you can land faster and you don't need the retro rockets, right?
Right.
Yeah. So.
And then the other part is, we don't necessarily in the U.S. have a good landing site where you wouldn't be overflying, cities and stuff like that.
And you don't want to land in Death Valley or anything like that.
Right. And one of the problems, and say if you tried to land in the desert, one of our issues is if there was a rock. And you land on top of a rock, you could actually injure the crew because it doesn't land the same way if you came down on top of a big rock as it did if you came down on a nice grassy plain.
Yeah.
So those are a lot of the reasons that we went back to landing in water like Apollo did.
Oh, okay. Yeah, well, it makes sense. So just kind of thinking about the mission of Orion, and I know there's like a lot of different tests that we can go over, but we'll have to do another episode for EM1 and like all that kind of stuff, because that we can really do a whole nother episode just on.
Oh, we can talk about how EM1 goes together for a long time.
Oh yeah. But kind of just ending on the idea of the mission. Like what is the end goal? Obviously we have 21-day missions, but you hinted at a gateway, a deep space gateway. So how does that fit into the Orion picture?
Right. So the big purpose of Orion is to be the architecture piece to actually begin a permanent exploration of space. So Apollo was awesome. I mean, no one's going to deny that. We landed people on the moon.
Right.
But that was all it was designed to do. And it didn't really set us up for long-term exploration. You know, we didn't have an outpost. We didn't have plans for what to do next. But Orion is really, and with the Space Launch System, you could then launch big pieces where we can start to build an outpost. So we can build a small little mini space station around the moon where we can start doing much more difficult exercises where the crew is out there for months at the moon, where you can't come home within hours from the space station and stuff like that. So it's a more of an engineering challenge on your design. And so we can start testing out some of those deep space exploration things, and then longer term you'll be able to start assembling a Mars vehicle out there. So we can start flying the pieces up, because to go to Mars, that's a 2-year mission. So we need a big habitat. You need a lot of food and a lot of water and big solar arrays. So in order to start testing some of those technologies you need for a Mars vehicle, Orion can help be a part of that lunar phase of now doing, you know, the testing and the vehicle designs we're going to need for the future. So it's really setting the stage for a long-term exploration. Of first, you know, we have the space station, which can test a lot of things for the crew. They're testing closed-loop designs. They're doing a lot of stuff like that. If we start building things out around the moon, we're now challenging ourselves for reliability and vehicle design, and not being able to come home quickly changes your perception a lot on how you design your vehicles. And then eventually using that as a staging ground for going to Mars and beyond. So that's really the vision of, you know, first you build a big rocket in Orion, and then we can keep building the other pieces to keep going. So Apollo was a focus, land on the moon, and that was it. Now we're trying to set the stage for a long-term exploration project.
And it seems like, I mean, I think, honestly, just from talking with a bunch of different guests on this show, International Space Station plays a huge role in that as well. Like, what we're doing and learning there can be applied to, you know, like you said, this outpost that's going to be around the moon, and then what we do and learn on Orion is going to learn for missions beyond, because now you're talking about the space camper going around the moon and having to be able to withstand having a crew there for up to, you said, 3 weeks. So
well, 3 weeks on Orion, once you've built a little outpost, you can stay for months at a time around the moon.
That's what I mean. Yeah.
And so as you've got to be able to build these pieces one at a time. Like, right? We don't have an endless budget. We can't do everything at once, which would be awesome if we could. But, you know, realistically, we need to make incremental steps. And as long as we're progressing, we're doing something.
Yeah. So, I mean, do you think Orion will play a role? I mean, it sounds like Orion's going to play a pretty decent role in this outpost around the moon. Do you think it'll play a role in a Mars mission?
Absolutely. So once you want to go to Mars, you're still going to use Orion to get to your Mars vehicle.
Oh, there you go.
Right? And you'll use Orion to get home from the Mars vehicle. You don't want to have to rebuild these things over and over. So really, by building Orion, you're going to keep building carbon copies in the future. And we've got some upgrades planned, so it's not going to all be, you know, one perfectly carbon copy. But for the most part, you've got your vehicle that safely gets the crew off the Earth and home again. And then, so that'll be used for those Mars missions to get the crew to the Mars vehicle. And then you'll go do your Mars mission, and then you come home again in Orion. So this it doesn't end.
Right.
Orion, like Shuttle, should be a multi-decadal program when it's all said and done, and you'll just keep using it.
Wow. Okay. I mean, it's just so cool to think that, you know, this is our plan. And it sounds like you were talking about in there, you know, we already have upgrades planned. You know, this is not the end-all, be-all. We're going to have to keep improving. This is how we do it, right?
Right. So, I mean, the hardest part is getting it to fly the first time.
Yeah.
And so, right, like I said, we didn't put life support systems on for EM1 because there's no crew. So the first obvious upgrade for EM2 is to put the life support system on. And so there's some things like that. You don't want to keep having to upgrade Orion, but there's a few things you can do to make it better. If you change the mission design, say you wanted to go to a low lunar orbit in the future, we'd need to add a sublimator to reject some of the heat, because it's actually kind of hot around the moon. So, you know, there's things we can do, and we're sort of protecting for those things so that if the changes happen, we don't really know exactly how those future vehicles are going to shape up. You can tweak Orion, and I wouldn't really so much call it as change Orion as tweaking it to make sure it's supporting the missions that you need. So we were protecting for a few things. We've got some space left so that if you need to add something, there's room to put a few more things on. And so it's just sort of undefined spaces, but that gives you opportunities to do those tweaks you need. You're not going to fundamentally change the shape or the parachutes or the reentry systems, but we have extensible capabilities that you could add on later.
Wow. All right. So, I mean, I've asked a couple guests before this, and I love asking this question. I think it's a good question to kind of end on is, you know, we're designing Orion to be a human space exploration vehicle, to take humans further out. And we have rovers that are already on Mars, orbiting around Mars, going to different planets. And yeah, that's cool. And there's a lot of robotic missions. But why humans? Why do we send humans out into explore the solar system?
So, I mean, there's the science answer, right?
Yeah.
You know, robots are awesome, but humans can do what robots are doing within a matter of hours.
Yeah.
Right? You know, a 6-month rover on Mars could be done in hours to days with humans because they can travel faster, they can see things, they can process things real time.
All right.
But then there's the humanity answer, right?
Yeah.
You know, all these things we're doing, it is to improve technology and bring humanity together. So sending people, having that challenge is a uniting force.
Yes.
So space exploration is still one of the only peaceful activities humans do. So I'd like to keep it that way.
Absolutely. We have an international space station already, and even Orion is an international effort, right? You already said we're working with the European Space Agency, and they have a critical component to make Orion possible, and can't do it without them. We need everyone, all hands on deck, and you're right, it's for a peaceful mission, so absolutely love that. Well, Najood, thanks you so much for coming on the show. And, I mean, that's a super high-level overview, but you know what? That's what more podcasts are for. More podcast episodes are for going into the details and stuff like that, but that is just, I thought that was a perfect explanation of what Orion is all about. So thank you so much for coming on the show. For those listening, if you want to stay tuned until after the music or credits here, we'll tell you how to follow Orion's mission and pay attention to the story on social networks and everything. So, Najood, thank you so much for coming on.
You're welcome. Thanks for having me.
Absolutely.
Houston, go ahead.
Stop of the space shuttle.
Roger, 0J, and I feel
Shuttle has cleared the tower.
Became a peace for all mankind.
Actually, a huge honor to break a record like this.
Not because they are easy, but because they are hard.
Houston, welcome to space.
Hey, thanks for sticking around. So today we talked about the Orion spacecraft with Najood Moranci, and we really, honestly, just kind of skimmed the surface. I had a lot that I really wanted to talk about with Najood, but we sort of ran out of time. And there's been one of the main things I really wanted to talk about with her today was, just besides the whole Orion thing, I really wanted to go over some of the tests that they've been doing. We'll probably follow up with an episode later about some of those tests. But if you want to go to nasa.gov/Orion and check those out now, there's a lot of them. They had water drop tests and egress tests and parachute tests, launch abort, whatever you want. Actually, we do have a launch abort episode coming up here soon. But if you want to check it out, just go to nasa.gov/Orion. You can find it out now. On social media, they're talking about all the updates and all the cool tests that are going on too on Facebook, Twitter, and Instagram. On Facebook, it's at NASA Orion, Twitter at NASA_Orion, and on Instagram, it's Explore NASA. All of them are verified, so you can find them pretty easy. But if you want to use the hashtag AskNASA on any one of those platforms and just mention Houston, we have a podcast, we'll get to one of those, some of those answers shortly. We have a lot of episodes coming up on all different topics, so we'll just try to fit that into one of the episodes later. So this podcast was recorded on September 13th, 2017. Thanks to Alex Perryman, John Stoll, and Rachel Kraft. And thanks again to Mrs. Najood Moranci for coming on the show. We'll be back next week.